In the previous chapter, we applied the Schrödinger's equation to solve for the hydrogen atom, and we had two major achievements. One was that the quantization for energy is now obtained as a natural condition to satisfy the boundary condition of the wave function at r equal to infinity. That's the same result as the Bohr model for the energy quantization. And the other thing was that we solved for the angular part of the wave function, which turned out to be the so-called spherical harmonics, and that is the same for all centrally symmetrical potential, including the Coulomb potential. Now, we did not have a chance yet to examine the physical meaning of the quantum numbers that we have discovered for the hydrogen eigenstates. These are the three quantum numbers, n, l, and m. So we're going to take a closer look at these quantum numbers, what's behind them, what's the physics behind them. And in particular, we're going to focus on the angular momentum, and why is angular momentum not only conserved but also quantized. And we're also going to examine the behavior of an atom if we put it in a magnetic field. What is it going to do? And also, we'll introduce an ever so important aspect, a quantum quantity called spin for the electron, which is responsible for many, many things, including the so-called fine structure of hydrogen atoms. It turns out that the energy diagrams that we got for just solving the Schrödinger's equation is only a crude approximation. If you look at all these eigenenergy levels in more details, you will find there is an underlying fine structure. So we're going to take a look at that in association with electronic spin. And we're also going to look at the significance of alpha. That is the fine structure constant which we introduced in the first lecture of this chapter. We're going to take a look at how important this fine structure constant is. So let's get started. Out of these three quantum numbers, the first one we are going to examine is the meaning of n, the principal quantum number. The principal quantum number only appears in the radial part of the wave function. And the radial part of the wave function is the only part of the wave function that actually depends on a specific form of the centrally symmetrical potential U. So it varies from Coulomb potential to a different potential. And we saw that in the case of Coulomb potential, this number n is the only quantum number responsible for the energy, for determining the energy of the system. And we call it the principal quantum number because it has to do with the ever so important quantity of energy. In fact, was the only thing that determined energy in the Coulomb case. Now, I must point out, however, that in the most general case of centrally symmetrical potential, n is not the only quantum number which determines energy. Another number that also helps determine energy is L. L, the second quantum number. And the fact that for the Coulomb potential, all L values belonging to the same n value will lead to the same energy is what's called accidental degeneracy. You know what degeneracy means, right? With different wave functions that get the same energy, that's called degeneracy. This degeneracy for different L values is not universal for all centrally symmetrical potentials. In fact, it is unique to the Coulomb potential. We call it accidental degeneracy. Why is that true? We're not going to deal with that here. I just want you to know that is the case. So in general, energy depends both n and L. But again, the principal quantum number is the only number that specifically depends, it specifically has to do with the radial part of the wave function. But let's take a closer look at the meaning of L. L is called orbital quantum number, and it has to do with the angular momentum of the system. Let's take a look at, first of all, the classical picture of angular momentum for a particle moving in a centrally symmetrical potential. You know, if a particle moves in a centrally symmetrical potential, then that potential does not produce, the force corresponding to that potential does not produce any torque because R and F are along the same line, so R cross F, the torque equals 0, therefore the angular momentum does not change, it is conserved. As in the case of the electron going around the proton, or as the case of the Earth going around the sun. Okay, so we write down the energy of the system is K plus U. U is just the potential energy, is a function of the radius R of the orbital, and this V here is the magnitude squared of the V squared is magnitude squared of the velocity, and the velocity has two components. So I'm going to divide this velocity into two components. You can see here. One is the radial component, which means the particle go in and out, in and out. And another is the tangential component called v theta. This is the component of the velocity perpendicular to the radius r. Now, so if an object moves in a circle, then r does not change. That means Vr is 0, right? Vr is actually dr over dt, so you only have v theta left. But in general, Vr does not have to be 0, so it can go in and out while going around at the same time. And Vr and v theta obviously are perpendicular to each other, so we have v squared equals v theta squared plus Vr squared. And why are we separating v into these two components? Because the radial motion does not contribute anything to the angular momentum, right? The angular momentum, you have to turn around. If you want to look for angular momentum, which is m r cross v, only this component v theta contributes. In fact, L, the angular momentum, the orbital angular momentum of this object going around the center, radius r, is m times v theta times r, not the whole v. And that's a constant because, like I said, there is no torque exerted by that force here, and therefore the angular momentum is conserved. So mv theta r equals L. Let me solve for v theta then. It's L over mr. So you see, I can use the conservation of angular momentum to get rid of v theta as a variable in favor of a variable r. So I don't have to deal with the motion around the center of the potential. I only have to deal with the motion towards it, away from it. I only have to deal with Vr. So plug that into here for part of the kinetic energy. So Vr stays, but U stays, but V theta is now L over mr, and you square it. Now what I want to do is I'm going to keep only this term in the kinetic energy, the term that has to do with Vr squared, the radial motion, and I'm going to combine the potential energy U with the term from the kinetic energy, which actually came from the tangential motion, which I re-expressed in terms of the conserved quantity, which is the angular momentum. So what I have arrived now is an expression for energy, which is the radial part of the kinetic energy plus this term, and this term is called this effective potential energy. It is made of two terms. One is the real potential, the actual potential energy, and the other is this term, which actually comes from the angular momentum, L squared over 2mr squared. This quantity, L, is conserved, so it's very convenient to write it this way. You don't have to deal with v theta, just r. And this term is always positive, as you can see here, L squared over 2mr squared. And it is called centrifugal potential. Centrifugal potential, because this term tends, being a positive potential, it tends to push the object away from the center here. And what is the importance of writing down E in terms of the effective potential plus the kinetic energy having to do with only radial motion? Because now we don't have to worry about the tangential motion. We can just focus on the radial motion, focusing on how r changes as a function of time. R changes as a function of time, governed by this energy, which means you can think of the radial motion of the object effectively as a one-dimensional motion in this effective potential. Okay, so if I only want to know how the distance between these two objects change, how r changes, let me plot the effective potential. The effective potential is made of two terms, the real potential plus this centrifugal potential. And from this effective potential, I can figure out how the thing moves radially. How does r change? For example, in the case of gravitational potential, U is a negative number, right? Negative g m1 m2 over r, that's the gravitational potential, plus a positive term, which is the centrifugal potential. Now, when r is large, this negative term, which goes like 1 over r, is greater than this positive term because the positive goes like 1 over r squared. For large r, the negative term wins. The overall potential is negative, and it gets more and more negative as we go in. But at some point, this term will overpower that term, and it starts to rise. Okay, eventually, when r is really small, of course, 1 over r squared is considerably greater than 1 over r for r very small, so it goes up like this again. And this is the effective potential governing the motion of an object going around another object due to gravitational attraction of each other. And the total energy is equal to this part plus the U effective. This part is never negative. Yeah, it is the kinetic energy associated with the radial motion. And the total energy, therefore, has to be greater or equal to the U effective, right? Because you have a positive term here. Now, this is the lowest point of the U effective value. So if the total energy happens to equal to this, okay, total energy happens to equal to this, what does that tell you about VR? VR is 0, which means what? It doesn't mean the object doesn't move, right? It means it doesn't move in this direction. It does not have any energy to move radially anymore, which means R never changes. So what kind of motion is it? Yeah, it's a circular motion. Okay, it is a circular motion. So that's a special case when energy is only this much. It can only move at a fixed radius or not away from the center of attraction. Now, if the energy is somewhat higher, so the energy is here, not minimum value, then from this point to that point, in between these two values of R minimum and R maximum, the total energy is higher than the effective energy, leaving this term positive, so that is possible, because it has to be positive, which means now this object can actually move with a variable distance from the center of attraction, going from R minimum to R maximum. Okay, so the orbital, therefore, is no longer a circle with fixed radius, rather it is an ellipse, and here's the closest separation between the two objects. Here's the furthest separation. And as I increase R, as I increase energy further and further and further, at this point, when the total energy is 0, that means the R minimum is here, but R maximum goes to infinity, so this time the object can actually escape to infinity, and the shape of this orbital is no longer self-enclosed, rather it turns from a ellipse to a parabola. Okay, when energy is positive, then the particle certainly can go to infinity, and in fact can come from infinity all the way in. When it reaches this point, however, the total energy equals U effective. Again, that's when VR equals to 0. It no longer can move any further in. It has reached a turning point, so it comes back. So you can go from infinity to the minimum separation here. And that corresponds to the case of a hyperbolic orbital. So these are results that we already know from classical physics, but this illustration is very useful at showing you how the orbital changes as the energy, total energy changes compared with U effective. So let's remember, the U effective has two terms, the actual U and this centrifugal potential L squared over 2mr squared. Okay. In fact, without the centrifugal potential, if you only consider this, then for the Coulomb potential goes all the way in, right? Like this, right? All the way to negative infinity. So if you do not consider that, then the particle will simply fall all the way into the potential well, which means it's going to, the Earth would then collapse onto the sun. And what's preventing it from doing that is this centrifugal potential. So the sun actually pushes it away, sort of. And again, the reason why is because angular momentum has to be conserved. Okay, so that's why there is a turning point here. It doesn't go any further in, which of course is a good thing. Now, if we compare the effective potential in a classical case with our quantum case, in a quantum case, we actually have the radial equation. The radial equation is the one that corresponds to what we just discussed, the radial motion. Okay, here is the kinetic energy having to do with only the radial variable r. Okay, this is a shorthand. It's actually something like 1 over r squared, and then partial r, then r squared partial r. That's what it is. Okay, it only has to do with radial kinetic energy. And then you have the actual potential energy, and you have this term. Now, I didn't make this up, by the way. Okay, this came from the solution to the Ch42 equation, which we studied in a previous lecture. And there was a lambda here, remember? There was a negative lambda here, and it turns out that lambda, negative lambda, has to equal to L times L plus 1, and so you got that. Okay, now if you compare this equation, the radial Schrödinger's equation, with the classical case, you find that here, this is the kinetic energy, this is the total energy, that must be what? The effective potential energy, right? U effective, but U effective had a real U here, which is this, plus a centrifugal potential. The centrifugal potential was L squared over 2mr squared in classical case, but now it is equal to L times L plus 1 h bar squared over 2mr squared. So if you look at the analogy between the classical case and the quantum case, you'll find that this is the this is the centrifugal potential contribution to the Schrödinger's equation radial wave function in the quantum case. And so they equivalent to each other. The denominator actually cancels out, and that tells you that the magnitude squared of the angular momentum in the quantum case in fact equals to L times L plus 1 times h bar squared. And if you take the square root, this is what you get. Okay, it is L times L plus 1 square root times h bar. This is the magnitude of the orbital angular momentum. So for this reason, we call L the orbital quantum number, having to do with orbital motion, which creates an angular momentum. This is not an exact derivation for the magnitude of L. What we did was we made a comparison between classical case and quantum case, but it is kind of simple and it's illuminating because it gives us an easy way to find the magnitude of the angular momentum. Now the magnitude of the angular momentum is a fixed number, see here. This is because we're dealing with an angular part of the wave function, which is spherical harmonic wave function. The spherical harmonic wave function describes a situation where the angular momentum is conserved because, again, the force is central. There is no torque provided by that force. So angular momentum is conserved. There's only a single value when you measure it. So therefore, the spherical harmonics is an eigenfunction of the angular momentum operator, which means the angular momentum will have a single measured value, and no matter when you measure it, you're always going to get this. To verify that, what you can do is to define an angular momentum operator. In fact, we defined it some time ago. In fact, in a previous chapter, we defined the angular momentum as an analogy to classical case, R cross P. R is still R, but P now becomes the quantum operator, linear momentum, negative IH bar gradient, remember? Three-dimensional momentum operator. And then we square it. Square it is just L dot L, the product, the dot product of the two vector operators. So that's that, right? Now it takes a little bit of effort to work this out, but if you work this out, and if you take this result and apply it to the spherical harmonics, YLM, you will find that indeed you get a constant times the same function itself, which means this is indeed an eigen equation for L squared. YLM is the corresponding eigenfunction, and this thing here is the corresponding eigenvalue for what? For L squared. And therefore you take the square root of both sides, you find that the eigenvalue for L is the square root of L times L plus 1 h bar. Okay, I never said that before, but we have seen so many examples of angular momentum. I want to call your attention to one important piece of information, that is the angular momentum in quantum mechanics is measured with h bar. The order of magnitude is h bar. H bar has the correct dimension, correct unit, and has the correct order of magnitude. Okay. So clearly this makes sense. As you see, it makes sense. Why is it that YLM is an eigen equation, an eigen wave function for the operator for angular momentum? Because the angular momentum is conserved. It doesn't change, and therefore it only gets you a single measurable value, and therefore, by definition, YLM is the eigen wave function for that operator, so it makes sense. So that is the meaning of L. It gives us an idea how much is the orbital angular momentum of the system, so we call it orbital quantum number.